Hey you guys, Mrs. Nzalako here. I am going to read out loud your review book assignment for this week. It is going to be, this part 1 assignment is going to be pages 38 through 44 with some review questions. Alright, as usual I'm going to be underlining important information and making some text annotations while I read. Topic overview. Throughout the ages, humans have observed the celestial objects in the sky and wondered about them. From Earth, a celestial object is any object outside or above Earth's atmosphere. There are about 6,000 celestial objects visible with the unaided eye from any location on Earth. Where do people fit? Are they alone? Are there other solar systems with an environment in which humans could live? This topic focuses on our solar system, our galaxy, the universe. In recent years, there have been much discussion of evidence of dark matter and dark energy, which may compose a major portion of the universe and our home Milky Way galaxy. Dark matter and dark energy are not presently a part of this course of study. Origin and age of the universe. Over the thousands of years of human thinking, various cultures have produced a multitude of theories concerning the origin, evolution, and structure of the universe. Universe means everything that exists in any place, all the space, matter, and energy in existence. The majority of scientists today think that the universe is extremely vast and that it is more than 10 billion years old, maybe as many as 13.7 billion years old. Presently, the majority of scientists believe that the universe began with an event called the Big Bang and has been expanding in volume ever since. The Big Bang theory states that all matter and energy started out concentrated in a small area, and after a gigantic explosion, matter began to organize into subatomic particles and atoms. Most, if not all, of the earliest atoms were hydrogen and helium. Within a few hundred million to a billion years, atoms became organized in celestial bodies, and then most stars became part of the gravitational groupings. As this organization of matter was occurring, the universe kept expanding in all directions and continues to expand at present. Evidence for the Big Bang. Scientists have theorized that if a Big Bang did occur, the energy created by the explosion expanded along with the matter. Thus, there should be a radiation from the Big Bang in all parts of the universe mixed with the energy given off by stars at later times. Recently, scientists have found evidence of long wavelength microwave background radiation that appear to be coming from all directions in the universe. This cosmic background radiation is evidence supporting the Big Bang theory. Other evidence of the Big Bang is found in the spectrum of the radiation emitted by stars. Look over the electromagnetic spectrum in the Earth Science reference tables. The various types of waves that transmit energy through space are called electromagnetic energy. Each element emits energy in specific portions, wavelengths, within the electromagnetic spectrum. Because the human eye observes different wavelengths of visible light as different colors, people can distinguish specific portions of the electromagnetic spectrum. When scientists study the spectrum of electromagnetic energy coming from stars and other celestial objects, they can infer which elements are in these objects. Scientists base these inferences on the comparison of the signature wavelengths produced by elements on Earth with those coming from the other celestial objects. Scientists have found that the position of characteristic of wavelengths or colored lines are shifted to either the shorter blue end, so I'm going to make note of that, shorter was blue, or longer red end, longer was red. Relative movement between wavelengths. This shifting of wavelengths is called the Doppler effect. The Doppler effect. If Earth and another celestial object are coming closer together, the electromagnetic waves are bunched together, resulting in a blue shift Doppler effect. If Earth and some other celestial object are moving apart, the electromagnetic waves are spread out, causing a red shift Doppler effect. The collective light from all the stars in all the galaxies, except for a few galaxies close to Earth, is shifted to the red end of the spectrum. The fact that almost all galaxies have red shift indicates that the universe is expanding in all directions. This evidence further supports the Big Bang Theory and the expansion from the initial explosion. In addition, the farther away a galaxy is from Earth, the greater the red shift. This fact indicates that the rate of expansion of the universe is increasing. Review question number 2. The age of the universe is measured in 10 to 20, 1. Thousands of years, 2. Millions of years, 3. Billions of years, or 4. Trillions of years. Number 3. Studies of the universe generally indicate that 1. Almost all galaxies appear to be moving away from Earth at tremendous velocities. 2. Few galaxies other than our own exist. 3. All galaxies are approximately the same size. Or 4. All galaxies are spiral in shape. Number 4. Background radiation detected in space is believed to be evidence that 1. The universe began with an explosion. 2. The universe is contracting. 3. All matter in the universe is stationary. Or 4. Galaxies are evenly spaced throughout the universe. Number 5. Which statement best describes how most galaxies generally move? 1. Galaxies move toward one another. 2. Galaxies move away from one another. 3. Galaxies move randomly. Or 4. Galaxies do not move. Number 6. The following diagram represents a standard spectrum for an element. The spectral lines of this element are observed in light from a distant galaxy. Which diagram represents these spectral lines? 1, 2, 3, or 4. Structure of the universe. In recent years, instruments such as the Hubble Space Telescope have allowed scientists to infer some basic structure to the known universe. Galaxies. The basic structural unit of matter in the universe appears to be the galaxy. A galaxy is a collection of billions of stars and various amounts of gas and dust held together by gravity. An average galaxy will have over 1 billion stars, and there are over 100 billion galaxies. Galaxies have been classified into a few types, largely based on shape, including elliptical, irregular, and spiral. Our solar system is a part of the spiral-shaped galaxy called the Milky Way galaxy. So, Milky Way is elliptical. Oh, sorry. Our galaxy is spiral. Called the Milky Way galaxy, which has over 2 billion stars. Figure 3.3 illustrates the spiral shape of the Milky Way galaxy. It also shows the position of our solar system between two spiral arms, about 2/3 of the distance from the galactic center. Stars. Along with dust and gas clouds, stars make up the majority of the visible matter. A star is usually a large ball of gas held together by gravity that produces tremendous amounts of energy and shines. There are many exceptions to this definition. Some very old stars are the size of planets or moons, and some stars no longer emit much radiation. The star called the Sun is the dominant gravitational force associated with Earth and the rest of our solar system. Energy production in stars. Most of the tremendous amounts of energy produced by most stars is the result of nuclear fusion in their cores. Nuclear fusion is combining of the nuclei of smaller elements to form the nuclei of larger elements, with some of the mass being converted into energy. As an example, the Sun converts hydrogen nuclei into helium nuclei with about 0.07% of the mass forming energy. There are many other types of nuclear fusion that occur in stars of different ages or sizes than the Sun. Nuclear fusion can only occur in extremely high temperature and high pressure conditions, like those found in star interiors. The energy of nuclear fusion in most stars is eventually radiated into space as types of electromagnetic energy. The characteristics of stars diagram. The classification scheme of grouping stars by surface temperature compared to their luminosity is shown in the characteristics of stars diagram in the Earth Science reference tables. Luminosity is the actual brightness of a star or rate of total energy emitted compared to the Sun. It is measured as absolute magnitude, which is a star's brightness at a standard distance. What we directly observe when we look at stars is the apparent brightness, which is dependent upon the star's absolute luminosity and its distance away from us. An analysis of characteristics of stars diagram indicates the star properties are not random. Of the hundreds of thousands of stars plotted on the diagram, stars appear to be grouped by differences in luminosity and surface temperature as reflected by color. Just as filament in a light bulb or the coil in an electric heater changes color with increasing temperatures, stars change color from red to blue as their surface temperature increase. So, red to blue as temp increases. Star types. Figure 3.4 illustrates the relative size difference in some of the star groups. The diameter of the Sun, a medium-sized star, is 109 times the diameter of the Earth. Most stars are much bigger than Earth, but some, such as neutron stars, black holes, and some dwarfs, are smaller than Earth. These smaller stars are actually shown too big in this diagram compared to the Sun. Giant stars are 10 to 100 times the diameter of the Sun, and the supergiants are 100 to 1,000 times the diameter of the Sun. Some of the star types commonly identified in the characteristics of star diagram are described here. Main sequence stars. About 90% of studied stars are located on the characteristics of stars diagram in a broad band called the main sequence. Most stars spend the majority of their life span as a main sequence star. Most of these stars are average size, and as the surface temperatures of the star increases, the luminosity increases. The luminosity increase from red to blue to white is mostly related to an increase in star size and the resulting higher temperatures. Our Sun is a main sequence star of yellow color. The smallest and coolest stars in the main sequence are the very common type of star, the red dwarfs. Giant stars. Red, orange, and yellow giant stars are a rare type of star but are commonly seen in the night sky because of their large size. 10 times or more the diameter of the Sun and their high luminosity. These low temperature stars represent a late stage in the evolution of medium to small size main sequence stars, when they greatly expand in size. Supergiants. Supergiant stars can be anywhere from 100 to 1,000 times the diameter of the Sun. These highly luminous stars represent the late evolution of stars much more massive than the Sun. Supergiants usually explode in a tremendous event called a supernova. The supergiant stars that are the brightest and exhibit the highest temperature are the blue supergiants. White dwarfs. Not all white dwarf stars are white, but they are all small, around the size of the Earth. They are hot on the surface and low in luminosity. They represent the last luminous or shining stage of low to medium mass stars. Black dwarfs. When a white dwarf cools and no longer emits much electromagnetic energy, it is a dead star, a black dwarf. Black dwarfs are probably very common in the universe because in the many billion years of the existence of white dwarf stars, many trillions of them have stopped nuclear fusion and no longer produce nuclear energy. Star origin and evolution. Stars, like many objects on Earth, have an origin of evolution of features and an ending. Figure 3.5 models star evolution as partly shown in the characteristics of stars chart in the Earth science reference tables. It is believed that stars originate from clouds of gas and dust molecules. These clouds were created from the masses that evolved from the original Big Bang and/or from the mass given off by the stars that have expanded, exploded, or otherwise given off mass to space. Gravity causes these gas and dust clouds to clump up, forming larger and larger balls of gas and dust molecules. When the mass of these spherical balls becomes slightly larger than the planet Jupiter, the gravitational contraction results in high enough temperatures and pressure to start nuclear fusion. Then the ball begins to shine or radiate large amounts of electromagnetic energy, and the star is born. The The evolutionary stages of stars after they spend most of their lives as a main sequence star depends upon their original mass. Most stars with masses similar to the Sun spend billions of years as main sequence stars and eventually expand to become a red giant. As the bottom part of the figure 3.5 shows, these stars show up most of the nuclear fuel and collapse to form a white dwarf and then slowly die, becoming a black dwarf. This process may take billions of years, and some stars created soon after the Big Bang may still exist. The evolution of stars with the original mass greater than 1.5 times the mass of the Sun is substantially different. These stars exist much shorter periods of time, approximately 100 million years. As the upper part of figure 3.5 indicates, these massive stars evolve into supergiants after spending time as a large main sequence star. They eventually explode in a supernova event and then rapidly collapse, forming a body of much smaller than a white dwarf. They are so dense the only neutrons can exist and a neutron star is formed. When even more massive stars collapse, the density is so great that it creates an extreme gravity field that allows no visible light or any other forms of energy to escape, and a black hole is formed. Review question number 9. In which group are the parts listed in order from oldest to youngest? 1. Solar System, Milky Way, Galaxy, Universe. 2. Milky Way, Galaxy, Solar System, Universe. 3. Universe, Solar System, Milky Way, Galaxy. Or 4. Universe, Milky Way, Galaxy, Solar System. Number 10. The great system of 200 billion stars to which the Sun and our solar system belong to is the Andromeda Galaxy, Large Magellanic Galaxy, Milky Way Galaxy, Orion Nebula Galaxy. Number 11. A star differs from a planet in that a star has a fixed orbit, is self-luminous, revolves about the Sun, shines by reflected light. Number 12. The Sun's energy is most likely the result of the fusion of hydrogen atoms, transformation of the Sun's gravitational potential energy to heat energy, burning fossil fuels, or radioactive decay of uranium and thorium atoms. Number 14. As the star color changes from blue to red, the surface temperature of the star decreases, increases, or remains the same. Number 17. A giant star has a luminosity of 300. Its color is most likely to be 1. Yellow-red, 2. Black, 3. White, or 4. Blue-white. Number 18. A white dwarf star has a temperature of 13,000 K. What is the probable luminosity of the star? 100, 10, 0.1, 0.01. And number 20. The nearest star to the Sun is Alpha Centauri. How does the star compare to the Sun? 1. It is much hotter. 2. It has a different color. 3. It has a higher luminosity. Or 4. It is much smaller in diameter.